Unit 2 Chemistry, Chapter 16, Part 3, looking at reactions involving redox and their effects. So first of all is corrosion. Now corrosion can be a big problem, particularly the corrosion of iron, because that makes rust, and rust has a problem in that it flakes away and allows you to get into the area underneath, and then you flake away more of that, and that can really cause problems, particularly on big structures. Also things which are close to the sea, because salt water speeds it up. Okay? To protect against corrosion happening, there's a few things we can do. One is that we can just cover the surface, so cover up the iron or whatever it is. We can either cover it up with paint or with plastic, or we can cover it up by making it into an alloy, and that alloy wouldn't flake away. We'd choose one that didn't flake away. Or we can cover it with a metal which is less likely to react. Okay, and therefore will react much more slowly with the water in the environment around them. A more chemical way of doing it is we can put what's called impest current cathodic protection. Essentially what we do is you put a very low current to give the iron electrons. Now what iron is trying to do here is give up electrons. If you keep giving it more and more and more and more, well then this reaction is not going to happen. Or finally, we can put something that is more easily oxidized close to the iron, so that the iron ends up being reduced instead. So if you give something like zinc, the zinc's going to be the one that will give up the electrons, the iron will take it, and therefore it's not going to give up the electrons and become the Fe ions. So to do this we would need to look at our reactivity series. Okay? These are our most reactive metals down through to our least reactive. Obviously that's not every metal, but they're the most common ones that you're going to come across. And we can rank them by doing tests, and we can say the most reactive ones are the ones which are most readily going to lose electrons, so be oxidized, which means they're better reductants. We can also talk about this in terms of their reducing power. So potassium on this list has got the greatest reducing power, platinum has got the least reducing power. Okay. This is also shown on the electrochemical series, which is in your data books. Okay, it's just shown the other way up. So here we have potassium. Lithium's actually slightly stronger, so this has got the strongest reducing power, or is the strongest reductant. Okay, so things which are very readily oxidized are strong reductants. Their cations, so Li plus or K plus, are very weak oxidants. Okay. The ones which are most readily going to act as reductants are ones which have got a small number of valence electrons, so group 1 or group 2 metals, okay, because they've got fewer electrons to lose and therefore are going to give them away much more easily. Now we can exploit this to do a metal displacement reaction. If you take a pure reactive metal and you put it in a solution with ions of a less reactive metal, so you put some magnesium into a solution of iron nitrate for instance, the magnesium will displace the iron, so you get the iron knocked out and you go from having magnesium as a solid and iron nitrate to having iron as a solid and magnesium nitrate. And we can use this little list here to tell us whether or not that's likely to occur. Okay, so if we have magnesium and we have iron ions, we can see that the iron ions really quite want to gain some electrons, and the magnesium really quite wants to do the reverse. Okay, magnesium is a stronger reductant than iron. Iron ions are a stronger oxidant than magnesium ions. When we look at it, what we're really looking for is what we call a downhill slope. So from if you draw a line from your two reactants, Fe2 plus to Mg, if that slopes downwards going left to right across your page, then you know that it will happen. So similarly, if you have zinc metal and copper ions, they will react. But if you had copper metal and zinc ions, they wouldn't, because then you'd get an uphill slope. Okay, the copper really wants to keep hold of those electrons that it's got.